Okay, so we got here, we got so we put the runway on the slope so that no effect of friction takes place. So if we put it up, then friction, the force due to gravity can pull it down easily. Friction will not play a role. And also, we can increase the distance. You see here, I've written down increase the distance in this particular case. Okay, sorry, increase the angle. By increasing the angle of the slope, this also increases the force. Yeah. Now what we've done is the last few steps. I've said repeat steps with changing weight. So what we're doing is we're taking the weight from the trolley, added to the hanger. Okay, and also we increase the slope at regular intervals. So take the weight from the trolley, put it on the hanger. So here we go. Take the trolley, put it on the hanger, and then we increase the angle at. Okay, and then we let it drop, and then we use step 1 to calculate the acceleration, which is step 1 is here, calculate the acceleration. Okay, and then we keep repeating it until we're done. So, and then we're going to plot a graph of f against acceleration, and this will tell us how they are affected, isn't it? Now let's move to the next one. Now this one here is very straightforward. Now EM wave is something that we need to know, guys. Okay, now EM waves. So EM waves, we have gamma, X-ray, UV light, which is ultraviolet. We have visible light, infrared, microwave, and radio wave. Now what I've done is I've done the easy stuff. Now light has already been given to us. We cannot mention light again. So visible light is gone. So therefore I've selected the easy ones. Radio wave, that's one mark. What do we use it for? We use it for communication. That's the second mark. Microwave, that's the third mark. What do we use it for? We use it to cook. This is the fourth mark. How easy it is. Now, this question is something that we messed up. Now, we can clearly see that sound is bending away from the normal, and we can clearly see that light is bending towards the normal. The question says why the refraction is different. Why is it different? Okay, why is it different? Now, the reason for that is because refraction is because there's a change in speed. So when the wave changes medium, it changes speed, and then we talk about what's going on. Now, light, we can see that light bends towards normal. This is because light is slowing down. We can see that sound bends away is because sound travels faster. So here are the theory marks. Okay. Now, this one. Okay. Now, which one is best to use underwater? If you have to communicate through large distances, which one's best? Now, look at the amplitude. The amplitude tells you which one is best. Okay, now the one is best is going to be the one that keeps its amplitude for a long period of time, and this is infrasound. Now, whales, they use infrasound to communicate through large distances. Okay, so infrasound, because of the large distances, its amplitude stays high. That's why we use it. Okay, now this one here is straightforward as well. What we have is we have light from the sun, from a star. We know the frequency already, put a tick there. We know the wavelength, we put a tick there. We know the distance, we put a tick there. The time we don't know, we put a question mark. Now we know that the equation that links speed and wave speed is this one, and we know that the other equation, speed time, is this one here. So two equations, and then we rearrange it. So what we do is the first thing is we work out the speed. This is meters per second. Okay, and then we use that speed to work out the time, which is distance over speed. Here you go, and then we get this many seconds in this particular case. You can actually see there's nothing crazy going on. We're using what we know to get those 3 marks. So you need to wake yourself up. If you've forgotten about the equation, okay, then fair enough, you forgot about the equation. Okay, but if you know the equation and you mess up the arrangement, then you need to wake yourself up. Now, this one here is something that we've done before. Now, if you messed up the definition for longitudinal wave and transverse wave after so many times, it means that you were not controlled. You have not controlled yourself, and you're letting yourself lose control. Now, longitudinal wave, its particles oscillate parallel to the direction of energy transfer. Transverse wave oscillations perpendicular to the direction of energy transfer. Okay, now we have three waves. We got UV, we have ultrasound, and then we have seismic wave in this particular case. Now, UV light, it is an example of transverse wave. Okay, now what is transverse wave? We've already defined this before. Now it is also an example of an EM wave traveling at the speed of light. Okay, now ultrasound, it is a sound. Now all sound waves, they are longitudinal wave. What are longitudinal wave? We've already defined it on the top. Now it is also a mechanical wave requiring a medium to travel through. So sound need a medium to travel through. Now seismic wave, there are two types. There's P wave and S wave. Now S wave, if I tilt the S wave, you see that S goes down, up, and down. So this is a transverse wave. Okay, this means that automatically the P wave is going to be a longitudinal waves. Here we go, done. Now this one is an easy question. Now this one is about finding the fish. This is about location. Location has to do with sonar, which is echolocation in this particular case. Okay, so you need to fix yourself up in this particular case. Fix yourself or lose control. Now we have this one here. Now this is echolocation. All right, so this is echolocation. All right, so what we have is, first of all, the wave goes down and are reflected. The words are reflected off the fish. Okay, and the time delay is used to work out the depth. The distance, which is the depth, is S multiplied by T over there. Okay, very good. Over 2, because the time is because it took twice as long. Okay, now next one we have this one here. Okay, now what we have now, wavelength. The wavelength is what? Wavelength is the distance from one point to the next identical point. So if I take this point here, for instance, let me just use this. If I take this point, okay, where's the next identical point? So this point goes up, so therefore it's going to be this point here. So this here is one wavelength. So therefore from this point to this point, this is the second one. From this point to this point, this is the third one. From this point to this point, the fourth one, and then we have a fifth one in this case. So therefore we have 5 wavelengths. Alright, now if you're still stuck on this one, let me show you another way to work this out as well, if you can't clearly see. So we got one peak to the next peak. That's 1, 2, 3, 4. Now look at that. There's 1 square, 2 square, 3 square, 4 square. There's 4 square. So what we have is from here to here, we have 3 square, and then we have 1 square left over. So therefore we have an extra 1. So therefore this is 4 wavelength, 4 peaks to peaks plus 1. So that's 5. So 5 wavelengths. Now wavelengths fine. So 5 wavelengths is 60 centimeters. How do we know if 60 centimeters? It's written here, 60 centimeters. So therefore 1 wavelength is 12 centimeter. Now this one's straightforward. Frequency times wavelength. The frequency we know, the wavelength we need to convert, and this is the answer that we need to get for 2 marks. Very, very nice and easy. Okay, now let's take a look at this one. Okay, so I'm going to do this part again for you guys. Okay, very quickly so that we all understand, so we can have our purple pen properly done. Okay, now we need so here's the spectrum. So write down the whole spectrum first: gamma, X-ray, UV, visible light, infrared, micro, and radio wave. Radio wave is currently out of the screen. Now we need a frequency that is greater than visible. So therefore, frequency greater than visible. Here you go, free frequency. And this one has the highest frequency. Okay. Next, we need a wavelength that is lower, that is longer than X-rays. So X-rays here, so longer than X-rays is going to be this part here. So therefore, the only answer is acceptable is a UV. Okay, so UV in this particular case, you can clearly see. Okay, now this one is the node. Now what we have is so in order for you to see the node, the UV light falls on the marking. The marking is going to absorb the UV light, and the marking is going to emit a visible light. So the visible light is the one you need to see. Okay, you can't see any other light except visible light. Okay, so UV light absorbed by dark blank mark nodes, then emits visible light for for you to see. Now, infrasound is very straightforward. It is a sound wave with frequency less than 20 hertz. We're going to move on very quickly, and this brings us to this one here. Okay. Now, this is something that you guys done in chemistry and geography. Okay. Now, remember the core, the core, the inner core and the outer core. Now, the question tells us here. All right. So the mantle, which is, you see what I've drawn, is hotter. Is hotter near the core than the crust. Why is this? Okay, that's the question. Why is this? Why is this? Okay, that's the question. Why is this? Okay, so why is it that the core, sorry, the mantle, which is here, you can see the inside hotter, closer than outside. And the first one is the crust is a solid. What? So what? It makes nothing. No, that's wrong. Okay, now the earth core is a liquid. Now we don't know if it's talking about the inner core or the outer core. Okay, because remember, so the core, the inner core and outer core, one of them is solid, one of them is a liquid. So we don't know which one it's talking about, so it can't be this one. Now it says here the earth is absorbing heat from the space. Now think about this. If the earth is absorbing heat from the space, then this here needs to be hot. Okay, but the question telling you that the mantle is hotter inside, not outside. So therefore, by logic, that's why I was using logic here, this is incorrect. Okay, this is incorrect. And then the question says, then the answer says the earth is radiating heat from space. Now it makes sense. Now if this here is hot and the heat here is going into space, what happened? This makes this part cold, and the only thing that is hotter is the closer to the core. It makes sense, okay, by logic. Now this next question is how the temperature difference affect this. This is to do with convection. Okay, it is one of the ways energy is transferred. Now the hot materials, the hot stuff, they rise up. Why do they rise up? Because they have a lower density, because they've been warmed up, and this causes the materials under the plate to move sideways. Okay, so there's something I've drawn here, which I'm going to show you again. So we've got the earth, we got, let's say, the stuff here. Now when the hot materials start to rise up, okay, so the things, what's happened on the way? So on the way up, you have to push against the plate sideways, because the hot materials are rising because of the lower gravity, sorry, not low gravity, low density, and so on and so forth. Okay, now this one's straightforward. Now the first that we need to remember is this equation here. So power is energy over time. Now remember that energy is work done, and work done is force multiplied by distance. So this is the second equation that we need to remember. And therefore, so instead of writing energy, we can just write F times D. Now we need to rearrange to find time. Okay, remember, find time. So FD over power. Now F we know. Look, Newton. So this is force. This is distance. We know. And then we got the answer straightforward. Okay, so hopefully this has been saved up into your memory, and we need to get all the marks again to make sure everything's fully planned properly. Okay, do not miss anything. Do not miss anything, otherwise you'll be missed.